Question 4 asks us a series of questions on the relationship between force, momentum, and change in time. We are given a ball striking a bat. The ball has a certain mass, and in each experiment, the initial velocity is the same. The initial momentum of the ball is its initial velocity times its mass. This momentum is in the direction of the ball's motion. The force exerted by the bat acts for a short period of time and changes the ball's momentum, sending the ball in the opposite direction. The graph shows how the final momentum of the ball changes as the contact time between the bat and the ball changes. We can see in general from the straight line that as the contact time with the ball increases, so the final momentum of the ball increases as well. And since the mass of the ball is constant and the final momentum increases, this means its final velocity increases with a longer contact time with the bat. First, we need to define impulse. Impulse is the product of the resultant force or net force acting on an object, and this comes from the bat, and the time interval for which the force acts. We can also define impulse as the change in momentum of an object. Next, we need to use the graph to find the average net force applied from the bat to the ball. Combining the two equations at the top, we get a new equation. The change in momentum is equal to the net force times the change in time. Now, finding the gradient of the graph is the change in y over the change in x. Rearranging our equation in green to solve for the net force, we get the change in the final momentum over the change in time, which is the change in y over the change in x for the given graph. So we could say that the gradient of a momentum time graph or a momentum change in time graph is equal to the resultant force. To get the gradient, first we need to choose 2 points from the graph. If we take these 2 points and put in their respective x and y values, we get 225 newtons as the average net force applied by the bat to the ball. And this is to the right, or in the opposite direction to the initial motion of the ball. Next, we need to find the ball's initial velocity. If we take the equation we used earlier, we can rewrite the change in momentum as the mass times the final velocity minus the mass times the initial velocity. Now we can use either of the 2 points on the graph for this question, but here we chose to use the data where the line crosses the x-axis, where the final momentum is 0. We can substitute 0 for the final momentum. We know the mass of the ball, which we must put in kilograms, so we get 0.15 kilograms. We are looking for its initial velocity. We know the average net force applied by the bat. We worked it out in the previous question. And we need to use the corresponding x value for a final momentum of 0, and this is a change in time of 0.01. Rearranging and solving, we get negative 15 meters per second as the initial velocity of the ball, but the question only wants the magnitude. So we can leave out the sign and just write 15 meters per second, and we know this is in the direction towards the bat. Lastly, we must redraw the graph for a larger ball mass. Here is the graph which was given to us, and it is for the smaller mass. And we must draw on these same axes what the graph looks like for a larger mass. We are told the initial velocity is unchanged, as well as the average net force applied by the bat. The only thing that has changed is the ball's mass. Now, since the gradient of the graph is equal to the net force, and we are told the net force is constant, we can deduce that the gradient of the graph we must draw will be the same as the graph given to us. It won't change. So we know the line we must draw will be parallel to the given line. Also, since momentum is a vector, if the initial momentum of the ball towards the bat is positive, then the final momentum away from the bat is negative. And so we know the intercept must be negative. So the graph cannot be starting above the x-axis. It must start below the x-axis. Momentum is equal to mass times velocity, and so increasing the mass increases the momentum, and this makes the final momentum value at a change in time equals 0 a more negative value with a lower y-intercept. And so the graph starts further down the y-axis. The graph we must draw is shifted downwards.